Yes. Okay. All right. We followed up with MeerKAT with a different band, UHF, and then if we get time, we'll talk about the MIGHTEE H1 aspect and how we're trying to bring together H1 and continuum studies in AGN, and it's really hard. Okay, so extragalactic radio surveys. You might know Moses, who is not here, I note, at the moment. Moses, I don't know if you're online. Noted. But basically, when you study a galaxy, whether it be active or not, whether it be an AGN or not, the different components of that galaxy, so the dust, the gas, the stars, the different components of the AGN, they will all emit at different wavelengths. And so in order to really understand one galaxy, one object that you're looking at, you have to observe it with a whole bunch of different wavelengths, different telescopes at different wavelengths in order to pick up those different components, to really know what's going on. And then, of course, to try and figure out evolution. So as you look at galaxies that are further and further away. But from this plot here, where we've got X-rays over here, we've got UV, we've got optical, and we've got infrared. This is a typical spectrum SED of a galaxy. What we're missing here is the radio, and that was kind of typically ignored in the past when we're looking at large extragalactic surveys. So you just look at a big patch of the sky, you look at it with several different types of telescopes, and radio was kind of not included in that because traditionally it didn't have as much the high enough angular resolution and sensitivity to be able to match with the optical galaxies or the infrared galaxies or whatever it might be. But that's changed now with telescopes like MeerKAT, that we can include the radio component on this. And usually it's just like this straight line power law. If you squint a bit, it looks like a straight line, and sometimes there's a blip at about 21 centimeters, which is your H1 signal. So exactly what do you see when you take a radio image of the sky, a radio survey of the sky? Well, it depends. There are I'll just hide this. Two different things. Depends on how you process your data. Either you can see spectral line emission. So you can see, for example, the signal of hydrogen gas, and that will give you a three-dimensional cube. So you'll have right ascension, declination, which you're all familiar with, and then the third axis is frequency or velocity or kind of distance of that H1 gas. And you can see a little signal there. And then if you integrate along your spectral axis, so you flatten it down like a pancake, you get an image. And this, when you look at an image, now we're looking at something completely different. We're seeing continuum emission. And this is coming from synchrotron radiation. And in the second part of the talk, I'll explain what is emitting that signal. But basically, for free, you get all of this information with one radio observation, and then how you process it will distinguish between whether you're looking at H1 spectral lines or whether you're looking at continuum. So first, we'll start off with the H1. So I've talked about radio surveys. How do we do that? Well, radio telescopes. Traditionally single dish. This is what I use for my all of my PhD research parks in Australia. And then you can't build telescopes infinitely big. So eventually you split them up into smaller telescopes, and smaller dishes connect the signals with fiber optic cables and the correlator, spread them out over a large distance, and you get an interferometer. So like the VLA, which I used as part of my postdoc research in Zagreb. And now, of course, we have MeerKAT, which is a newer generation one and a precursor to the almighty SKA, which we know is coming very soon. And so MeerKAT has proven to be excellent for galaxy evolution studies, large radio surveys, both in H1 spectral line and in continuum. So I don't think we need to talk much about what MeerKAT is, but hopefully you know most of this. It's 64 dishes of 13.5 meters in diameter. The key thing is that there are two bands that it can observe. And so if you're not a radio astronomer, that might be confusing, but just think of it as two wavelengths. We talk in frequency space in radio astronomy, wavelength ranges. So we've got L band, which is the higher frequencies. So that's smaller wavelengths. And then that takes us out, if we're talking about H1, to a redshift of about 0.58. And then we have the UHF band, which stands for ultra high frequency, but is a misnomer because it's actually lower frequency than L band. So that takes us between redshift 0.4 and 1.44, so longer wavelengths. And there is also an S band, but I don't use it. That's kind of newly commissioned and we don't really, I haven't used it yet. So mostly MeerKAT spends its time doing these large survey projects or LSPs. And there is limited open time also available. So most of our work in Radiance uses two big LSPs and a little bit of open time data. So here are several of the LSPs, or maybe it's all of them. The ones that we use are LADUMA, which is a H1 survey only, and MIGHTEE, which is both H1 and continuum and polarization. Okay, so part one, neutral hydrogen gas with LADUMA. So just so we're all on the same page, H1 is atomic neutral hydrogen. This is a predominant element in the universe, and the hydrogen atom, when we say neutral, it means it hasn't lost its electron, it's not ionized. And you have in the hydrogen atom, you have a proton and an electron, and they have this quantum property called spin. And so this property can be the same for both of them. Let's call it spin up or aligned. Or one of the spins could be in a different direction where therefore the spins are misaligned. The aligned state has slightly higher energy than the misaligned state. So this can be either excitationally, collisionally or spontaneously de-excited from the high excitation aligned state to the de-excited misaligned state. And in order to do that, it has to lose some energy. So it emits a photon of wavelength 21 centimeters, which is at 1420 megahertz, which is nicely in the band that we're observing with MeerKAT, especially when it's redshifted. And what does that look like? Well, if we can resolve it nicely, this is MeerKAT here, and we're looking edge on to this galaxy, and it's rotating so that the upper arm is going this way and the lower arm is going this way. So one arm is receding from our view and one is approaching us, or vice versa, whichever way. Then part of your X1 signal is going to be red shifted and part of it is going to be blue shifted, okay? So that's why you have this broadening and there's these peaks, and that's because of dark matter rotation profiles, which we're not going to talk about now, but you end up with this double horned spectrum profile, okay? So that's what the H1 spectrum of a galaxy looks like. This is kind of what an H1 image sort of might look like. Is it possible to get these lights at the front turned off? Oops. Oh. Okay. Cool. Thanks, Angus. This is one of the first images from Mongoose, where in the background you can see all the stars of a galaxy, and you can see the extent of this particular galaxy is this one here. But then the H1 is this faint red you can see, and it's extending out all the way out here and encompassing this little dwarf thing here. So H1 is thought to play a very major role in galaxy evolution, we think, although that could be wrong. It's very good for tracing the outer parts of galaxies. As you can see here, the H1 disk extends out much, much further than the optical disk, or it can. And because of that, it's less gravitationally bound on the outskirts, so it can trace interactions more easily. If you've got an interaction between two different galaxies, this H1 can be disturbed, and it can be a good tracer of those interactions. And the cold gas is also very, very important because it's the raw fuel for star formation. So if you have a galaxy without any hydrogen gas, it can't form stars, because of course stars are formed from nuclear fusion starting in cold hydrogen gas. Okay, but the problem is that it's quite a faint signal. This 21 centimeter signal that I'm talking about, it's very faint and it's difficult to detect beyond the local universe. So we can't really see how the H1 content of galaxies evolve with redshift. And does this track this is our favorite kind of cosmic noon plot, where we know that most of the star formation in the universe happened at about redshift 1 or 2, and then it's been decreasing ever since. Does that correspond with a matching change in the H1 content of galaxies? Yes or no? It's very hard for us to tell. So we're trying to push the redshift boundary out to which we can detect this H1 signal. So that's something that is one of the primary goals of LADUMA. So when you do extragalactic surveys, you usually take this wedding cake sort of approach, where some surveys will be wide field but shallow and low redshift. Some will be narrow field and very sensitive, very deep, high redshift. So LADUMA is kind of this point right up here. It's the deepest H1 survey with a single pointing of MeerKAT, aiming to reach out to redshifts, or capable of reaching out to redshifts 1.45. Will we detect anything out there? Jury's out. Okay, so this LADUMA stands for Looking at the Distant Universe with the MeerKAT Array. One of the PIs of this is Sarah Blythe, our head of department at UCT. And we want to look at the H1 properties of galaxies and how they evolve out to high redshift. Okay, that's the main point. The rest you don't need to worry about. It's just one pointing at the sky. What is its current status? Well, first of all, what do you do with a survey? You have to get the data. So we've got some of the observations with MeerKAT in L band and UHF band. UHF is because, of course, we want to go to high redshifts where the H1 signal has been shifted all the way into the lower frequencies, which is why we need UHF band. But at the moment, we're just playing with L band and the lowest frequency, the highest frequency range, so the lowest redshift range, just to see if we can know what's going on there. And then we'll apply those lessons to the higher redshift data. So once you got the data, then you need to make your data cube. Okay, so here is an image of one channel of LADUMA, an early LADUMA cube. I'm going to play the movie, so it's going to step through different channels, different frequencies, and you can see the little dots popping up, and they are little H1 galaxies, okay, H1 detections. So if you're a radio astronomer, you can read these values and it might mean something to you. If it doesn't, don't worry about it. But basically, we have a really nice dirty cube. Yes.
So it's a question from an astronomer. So seriously, you have no other ones?
You do. There is actually one, which is OH, so hydroxyl. And you can detect, for example, megamazes with that. And in fact, LADUMA has detected one of the highest redshift megamazes. I'm ignoring that completely because that's not our science, but that is, as far as we know, the only other major line in that region. Yeah, but that's a great question.
Is it very different weapons, so you don't use it?
Yes, yeah, very different. I mean, if you have a detection and you can find the optical galaxy and you can find the redshift of the optical galaxy, then you know which line it is. Otherwise, it could be either. Yeah. Yes. So, and we're just cleaning. So, if you're a radio astronomer, that means something to you. That's great. We're in the final stage of cleaning the LADUMA cube in L band. Otherwise, don't worry about it. We're still working on it. And then the final step is once you have your cube, you need to go and find the sources in it. All right. You have to go and find, we're going to ignore the OH, so the H1 detections. How do we do that? Well, we can go through the cube like this by eye and look and just point to them and find it manually. This is only a tiny frequency range. And I'm zoomed all the way out. What you have to do is go through the whole frequency range and zoom all the way into the cube in all the different parts in order to see the good enough resolution to find all the galaxies, which we did. So I'm one of the leads of the source finding working group, and a bunch of people did that by eye. It was very painful. We're not going to do it again. This data is huge. So we've moved on to trying to do this with an automated code, which is called Sophia 2. And Leia's, part of Leia's master's project is trying to get Sophia 2 working on the LADUMA data, which she has done very successfully. So just to show you what I mean here is that here is one frequency channel, here is the next one, and the next, and the next. And one single galaxy can appear in several different channels because you've got parts of the H1 gas moving at different speeds within the galaxy, especially if it's rotating, and that's why you'll have a detection in several frequencies, and then it drops out at one of them. Okay, that's Leia's work. Okay, and so what have we found so far? 185 galaxies with H1 in the LADUMA field in the data. Here are their positions, color coded by, that's frequency, right? Yes, good. And here another view is their H1 redshifts. So this data goes out to redshift 0.05. So for optical astronomers, you'll laugh and say, throw out all of that data at that low redshift. But for us, that's like, ooh, look how many we're detecting out to that higher redshift now. And of course, we go a lot deeper with the rest of the data, but that's still being processed. These H1 masses are not quite correct. We haven't primarily been corrected yet, but just to give you an idea of the range that we're looking at there. And here are some nice images because we all want to see some images. So we found some beautiful H1 disks. So you can see the optical galaxy here and how huge the H1 disk extends around that. We found some low surface brightness galaxies, and the H1 is very clearly detected, whereas in the optical, it's a lot more difficult to detect. We found some galaxies that are clearly interacting when you look at the H1 contours, here and here. And we even found an extended H1 tail, which is probably due to the interaction of these two galaxies, kind of ripping off this huge tail, just like the Magellanic string going around the Milky Way, ripping off the LMC and the SMC. And now Leia is using those early detections from the early science to do some actual science. So her goal is to look at the scaling relation, so just the relationship between H1 content and the star formation rate history. So the history of how stars were formed in the galaxies, in the optical counterparts to these galaxies, right? So for example, here you take your detection of H1, you go and find the optical galaxy, you measure the photometry in every band, you then fit the SEDs, and the SED that the best fit template SED that fits will correspond to a given star formation rate history, and then you look at the relationship between its H1 mass and its star formation rate history. So that's ongoing work that Leia is doing at the moment. She's busy extracting all the photometry and doing the fits. Okay, so MIGHTEE continuum. This is part 2. So hold on to your hats. We're going to do whiplash and change topics completely. So we were talking all about H1, and now we're going to switch and we're going to be talking about the continuum. All right, so just think, integrate down across all of those frequencies and you get continuum, the continuum map, synchrotron radiation. All right, so what is that? What are we looking at now? Something completely different. So you start with your MeerKAT L-band observations and you get data at a range of frequencies. You squish along the axis or integrate over all frequencies, and then you end up with a continuum map. And then each dot, I'm hearing somebody online here. Okay, if you could just mute yourselves. Thanks. So each bright dot here is emission from a galaxy. And this is not H1 anymore. This is now synchrotron radiation, which is highly charged particles traveling highly relativistically in a magnetic field. And when that happens, they spiral around and they emit this synchrotron radiation, this continuum power law radiation in the radio frequencies. So what can cause synchrotron radiation? Two main things. Star formation, really strong star formation in galaxies. Star formation equals the most massive stars die in supernova explosions. Supernova explosions kick out electrons to close to the speed of light. Well, relativistically, they interact with the overall magnetic field of the galaxy, releasing synchrotron radiation. So one of these dots, for example, could be a star-forming galaxy. Then another dot could be an AGN. So that's the second process that can release radiosynchrotron, are the radio jets of an AGN that happens to emit in the radio, and we call these radio galaxies. And it's these, the black hole is basically spewing out these accretion onto the black hole is all weird, twisted up magnetic fields there mean that this synchrotron radiation is spewing out in these kind of two beams like this here. And so some of these dots will be star-forming galaxies, some of them will be AGN, and we have to try and figure out which is quite difficult. And of course, some of them can be both. But we are going to only focus on AGN. And we are hunting for the biggest AGN, the giant radio galaxies. So first, a little bit about AGN, because a lot of the times optical astronomers don't realize this one very important fact. So if you remember, the different components of an AGN and their host galaxy emit at different wavelengths. So for example, if you've got the black hole in the center, your accretion disk around that will, let's say, predominantly emit in kind of optical UV continuum. And then we have a corona of plasma around that, which will emit in the X-rays. You'll have these clumpy clouds, which can emit optical emission lines, so the broad line region and the narrow line region, which you'll see in optical spectra. Then you've got your dusty torus that will emit in the, let's say, the mid-infrared. This is like a black body in the mid-infrared. And some AGN, but not all, have radio jets. Okay, so that's these synchrotron jets that I was talking about, the synchrotron emitting plasma. And if it does, then we call it a radio galaxy for short. Now, some radio galaxies obey the unified model, as we see here. So they've got several of these components, an accretion disk and a jet. And those we call HERGs, high excitation radio galaxies. But some radio galaxies don't obey the unified model, okay? So because they don't have an accretion disk. So if you have no accretion disk, you have no high energy photons to kind of ionize and do inverse Compton scattering in the plasma, so you have no X-rays. You have no UV photons to be absorbed by the dust to be re-emitted as infrared. So you have, oops, so, oh no, okay, I'm doing that. Blah, blah. Okay, I'll go to the broadline region. If you've got no UV photons, you've got nothing ionizing this region so that it can't de-excite and create emission lines. So you've got no broad, no narrow line regions and nothing being absorbed by the dust to re-emit in the infrared. So you have no infrared emission. But you still can have the radio jets because they don't rely on the accretion disk at all. Okay, this is an independent process. So we don't really know, but so there is accretion still going on, but we call it low excitation and sort of inefficient accretion, because probably, well, one of the models at the moment is that it could be this Bondi accretion where you've got this hot gas kind of trickling in from the halo and accreting onto the black hole that way, but it's not a whole bunch of matter coming in with this angular momentum, creating a nice flat disk with lots of friction, which is causing the bright sort of optical UV. But we don't really know, right? But there is this something, the black hole has to be eating something in order to be active. So it is accreting something, but maybe just not in this bright disk. And then you end up with these jets. So some AGN can only be identified as AGN in the radio. Okay, and we call these LERGs, low excitation radio galaxies, which Nagas has recently found out exist, and that a lot of the time the AGN community based in the other wavelengths is not aware of. Now, these radio jets can penetrate out beyond the host galaxy. So, for example, here's a host galaxy. Here are these massive radio jets, and they can grow out with age, probably. They can collide with the intergalactic medium, which totally looks like this, which is like, you know, hot ionized gas around there out on between galaxies. And when that happens, you can, you know, the jets slamming into this boom and creating this kind of hot spot there and there. And then that plasma can sweep backwards in these kind of backflows, which create these fuzzy lobes. Okay, so that's possibly one scenario of what's going on here. And so this is what we kind of see in this textbook kind of nice, beautiful Cygnus A, where you've got the core and the entire host galaxy will be in there. So all the stars are in there. You've got these collimated jets, and then you've got these hot spots here and these lobes here. Okay. Think of it like a whale's blowhole, sending out a spurt of water, which is collimated, and then it kind of goes all fuzzy after that. And we think that, yeah, these jets can grow outward with age. Now, giant radio galaxies are the biggest of these. So where from end to end, the jets are bigger than about 700 kiloparsecs. So just to put that into context, so this was Cygnus A, and that is not a giant radio galaxy. That is about 0.12 megaparsecs in size. Here is one that's starting to be on the cusp of a GRG. And then this is the biggest known ever. This is found last year, I think. It's called Alcyonius. About 5 megaparsecs in size. So these are huge, huge objects, well over, I don't know, 62 times the optical diameter of the Milky Way. And most GRGs are actually LERGs, so you can only detect them in the radio, and my battery is dying. Oh, yeah. Okay, so because the giants, if we think that the jets are growing outward with age, then one theory is that the giants are actually the oldest radio galaxies. They've had enough time to grow to those massive sizes. And so, yeah, that might be why they're so big. But surely there's other components that come into play. Maybe their environment, are they in less dense environments so that the jets are not inhibited and they can grow out to huge sizes? Is the AGN power, you know, the accretion of the black hole, the power of the black hole, is that playing a role? Maybe, but kind of the results are inconclusive. We've actually found GRGs in a whole range of environments with a whole range of jet powers. And the second question, so why really are they so big? And then the second question is, why are they so rare? Millions of normal sized radio galaxies have been found, tens of millions, but only about 3,000 GRGs. And this number actually jumped up from only 820 in 2020 to 3,000 in the last few years once the LOFAR telescope started working and found a whole bunch more. So where are the rest of them? Do they not exist? If these are just the biggest of your normal radio galaxies, then we really should be detecting quite a lot more of these. So do they not exist, or are we just not detecting them? So enter MIGHTEE. I think I want to skip this slide. I'll go to this one. Okay, so MIGHTEE is the MeerKAT International Gigahertz Tiered Extragalactic Exploration Survey. It's one of the LSPs with MeerKAT. It is a galaxy evolution project. It's covering 4 different fields. You don't need to know about the names, but in the early science release, which came out in 2022, it targeted 1 pointing in the cosmos field, which you might have heard of before, and 3 in the XMM LSS. It has an H1 emission and absorption component, which we might talk about if we get to part 4. It has a continuum component, which I'll be talking about now. And it also has a polarization component, which I won't talk about. It's in L-band and will be in S-band. I think all of the L-band data, I think, is taken. No, that's not true. But very few of the S-band data is taken. I will be talking about some of the L-band data. And here is the early science MIGHTEE Cosmos image. Now, if you have a look carefully at this, see if you can spot the 2 giant radio galaxies that we found there. I'll give you a few seconds to do that. Who thinks they're found too? Okay. Okay, I'll show you where they are. Here is what I creatively named GRG1. And here is GRG2. Oops, that one's a little offset. Okay, well, anyway, you can see it just there. That's there. Okay, and so these are actually really huge ones. They're about 2 megaparsecs in size. Here, the optical galaxy is right there in the center, and then you've got these huge jets and lobes, and you've got some hotspots in GRG1 there. And so we published that in 2021. The cool thing about this is that these giant radio galaxies hadn't been found before, even though the field had been observed with very sensitive observations with the VLA. Only the cores of them had been detected. So here I'm flicking between MIGHTEE, MeerKAT data, VLA high resolution data, and then the VLA with smooth to a match resolution of MeerKAT. Because VLA has high resolution, MeerKAT has lower resolution of 8 arc seconds. So here we have MeerKAT, here we have VLA match resolution, here we have VLA high resolution, and then we flip back. Okay, so you can see that only the cores are detected in the VLA, and then the lobes and the jets are completely invisible. Maybe if you squint carefully, you can see this hotspot of GRG3, but there was GRG1, but there was no way that we could identify them as matching to this core, and so they weren't identified as giant radio galaxies. So the lobes are completely resolved out. They don't exist in the data of the VLA because of the configuration of the antennas. It doesn't pick up those spatial frequencies. There's no way you can recover that emission. But with MeerKAT, we have excellent point source sensitivity, meaning that, the traditional meaning of sensitivity, but also it has the configuration means that it has excellent instantaneous UV coverage. So it can detect a whole bunch of spatial frequencies, small scale and large scale at the same time, which is why we can detect these fuzzy bits. Okay, and so this is a PD diagram. It's not so complicated. It just is here is showing you the size of radio galaxies. So bigger is over here, and here is the power. So fainter or luminosity. So fainter is down here. And I'm showing you just the known GRGs at the time that I published my paper, which was 2021 at the time. So those are the green and the black dots. And these tracks are showing you predicted evolution tracks, where you start over here, and then after about 100 mega years, you get the next triangle. And this is starting at a lower initial jet power, higher, and where you predict them to be after a certain amount of time. So I'm only showing you GRGs, so that's why there's only points above 700 kiloparsecs here. And there's lots of galaxies here, but I just haven't plotted them. Here is where GRG1 is sitting, and here is where GRG2 is sitting compared to the other ones known in the literature. So what we see here is that they're actually larger than about 93% of other known GRGs, but lower power. So they're sitting in this previously unoccupied part of the PD diagram. They're beyond the surface limit of this survey called LOTS, which was performed with LOFAR. And that's why nothing had really been detected there, because the telescopes just really couldn't get into that part of parameter space. But with MeerKAT, we're able to access it and probe a new part of galaxy evolution parameter space. I'm going to skip the statistics, but long story short, this implied that GRGs are actually much more common than we previously thought. We just couldn't detect them because of telescope limits. And that has now been found in the literature, and the number has grown massively, as I said, from about 800 to about 3,000 in just the last few years. So I was talking about MIGHTEE early science, and now this is the field. And now I'm going to switch to DR1, which covers a larger field. So Cosmos, XNM, LSS, you can see how those fields have grown, and we have this extra one here called CDFS. Okay, so now what we want to do is look for more GRGs in the rest of the data. So this is the master's project of Indibor, and he is searching the rest of these fields for more GRGs. And so far he's found 5 that have been confirmed with spectroscopic redshifts and 2 candidates. So here's an example of one beautiful big one, where if you have a zoom in of the optical galaxies here, you can see that there's this nice spiral, this galaxy here and a little guy there, and they're probably all interacting. The redshift errors are such they overlap, but they're not very good. So we probably should get some spectroscopic redshifts to try and determine if they really are interacting. And that could actually be triggering the AGN and these jets, but who knows? Here is an example of a wide-angle tail galaxy where your jets, which usually come out kind of, what do you call that, opposite each other? They kind of get pushed back as the galaxy is moving through sort of an intergalactic medium. This is creating this wide angle here, or this wide angle here, I guess. But even so, from end to end, this is more than 700 kiloparsecs, so it still classifies as a GRG. You can see that from here to here to here will be a lot bigger than that. And here's a few more with their little hosts. So that's what Indibor is working on at the moment. He's found them, now he's characterizing them, and he's going to do a spectral index analysis, which we'll talk about more in a moment. And here's the same PD diagram that I showed before, but with all of the known GRGs now to date. And this is GRG1 and GRG2 that I showed you from my paper. The black ones are all of Indibor's points. This line here was that if you remember the limit where there was almost no detections down there, and there was no GRGs down here except for GRG1 and GRG2. And you can see now this part of parameter space has been filled in hugely with the LOFAR telescope, with all of these newly discovered GRGs. And a couple of those of Indibor's new are down here as well. And there's this other red one here, which I'm going to talk about in a moment, which is Kathleen's project. Which brings us to what I'll probably end on part 3 now. So this is UHF Cosmos. So we have L-band observations of the Cosmos field with MeerKAT. This is where we found those 2 GRGs. And now we looked at it, we used open time data to point MeerKAT at the same field, but using the UHF band. So this is lower frequencies. And we created a continuum map at lower frequencies. This is about 800 megahertz, and yep, there's details, great. We can clearly detect the two GRGs in the UHF band. So there's GRG1, there's GRG2. I can flick between them so you can see how those, the fluxes change there. We expect it to be brighter at lower frequencies, and they are. But then at the edge of the beam, because at lower frequencies, your beam size gets bigger, we've actually found another third giant radio galaxy in the field. This is GRG3. And that's that one there. So that is at a size of about 1.3 megaparsecs. So this was the honors work of Kathleen Charlton, who is now gone on to her master's and is working on something slightly different, but finishing up an excellent paper on this. So you can see this is GRG3, in the background is the optical galaxy there, and you can see the radio contours going all the way out here. Now this one was concerning us, this optical galaxy here, it could be the cause of these radio contours, but actually we don't think it is. We think that this is all part of the jet of this GRG. And what Kathleen did is she took the L band image, she took the UHF band image, the two frequencies, and then she just divided them by each other to get spectral indices. So a spectral index is just basically if you are having a look at, here's your UHF band, 800 megahertz, here's your 1.2 gigahertz, you measure the flux. You measure the flux there, you measure the flux there, and you find the gradient between those 2 points. That's the spectral index, that's it. And so here I should have matched the colors, but Kathleen is showing the spectral index where you've got flat spectral indices kind of around 0 are the bluer colors, like the core and the hotspots. And then the red, the whiter and weaker and bluer, redder colors, sorry, are steeper indices. And you expect that where you have the electrons being accelerated, so near the black hole, and then re-accelerated when they hit the intergalactic medium there, you expect the spectral indices to be flat. And where they're old, they've lost energy, you expect the spectral indices to be steeper. And so the point of creating spectral index maps is to try and figure out the age of the electrons and therefore the age of the jets. And then, so, you know, try and figure out more about the actual physical characteristics of these things. So that's what Kathleen's been doing. Unfortunately, I don't have time to go into a lot of detail, but here are the spectral index maps. Sorry, ignore the table on the bottom. Here are the spectral index maps of those 3 GRGs with a matched range there. GRG3 is weird. It's a weirdo. We've been trying very hard to figure out what's going on here. Don't know, but we are almost cracking the case, we think. And then from the spectral indices, you can calculate ages, so spectral ages. And so here on this axis now is the age of the electrons in mega years, going up to, what's that? 4 at the top there, mega years old for some of these electrons there. And we've got some ages, and now we're writing the discussion. Yeah.
The age is since it was present.
Exactly. Yes. Yeah. So the electrons will lose energy over time, and the spectral index will steepen. Okay, so I'm going to skip part 4 because there's not much to talk about there anyway. But the point of this was that we are also using the not only MIGHTEE continuum, but also the MIGHTEE H1 data, because remember, you get both for free when you do an observation. And now we're trying to look at the H1 content of AGN. And this has pretty much never been done before because, well, we're not sure that there is any H1 in AGN. Surely this has all been like blown out by the jets. Well, we're not just looking at radio galaxies, we're also looking at non-radio detected AGN. But in any case, maybe the quasar mode, the heating has heated the gas and it's no longer neutral, or is there? We don't really know. It's very hard to detect. You can't really just do this with a direct observation and make a detection or a non-detection because there will be we think there's very small quantities. So instead, my PhD student, Tumelo Maniana, is using a process called H1 stacking, which I won't go through in detail, but long story short, instead of observing one galaxy for a long time to get a detection of H1, you can observe a whole bunch of galaxies for a short time, extract their spectra, align them at redshift 0, and then take the average, and that's called stacking. And so when you stack more and more and more galaxies, what started off as just noise, the noise is reducing by hopefully 1 on root n until you can make this statistical detection here. And so Tumelo is trying to make statistical H1 detections. Sorry, let me just say that again. Tumelo is trying to make these statistical detections of H1 gas in AGN. No luck so far, but we're working on it. And then I just straight up didn't finish this slide. Sorry, Kathleen. But Kathleen's now working on H1 absorption, which is again trying to determine whether or not there's H1 in AGN systems, where you start with a radio galaxy, which is really bright. So you start with continuum, radio continuum. We use detecting synchrotrons, so you know there's a radio galaxy there. And then the continuum light travels through space towards our telescope. If it goes through H1 gas, the part of the continuum that corresponds to 1420 at that redshift gets absorbed and then continues on to us. So you see an absorption spectrum in the spectral cube, right, at that position. But hunting for these absorption signals is really, really difficult. It should be easier to detect absorption than emission, but it's still really hard to find them anyway. So Kathleen's working hard on that, and she's just started her master's, so that's what she'll be doing. And that's it. Basically, I'll leave my summary here, summarizing our radiance research. Galaxy evolution, MeerKAT's amazing. AGN are cool. H1 is cool. We're going to combine the both. Thank you.
Thank you. Excellent talk.
Thank you.
Any questions? Nikki.
Hey, thanks for being very nice talk. I have a question about your GRD. So I noticed that most of the examples you were showing are pretty much perfectly edge on. So this is the right word to use for this kind of thing. Do you sort of handle of those the range of inclinations that you are detecting? You are missing out of the
Absolutely not. So we can't tell at all what the inclinations are. So what we're looking at is projected linear size. So if your eyes are a telescope and the jets are in this direction, well, they're going to look kind of small to you, but now they're going to look really big. So yes, of course, we're going to miss out on all of the galaxies with high inclination, which makes their lobes look kind of smaller in size. But then, of course, you've got your relativistic effects where one jet's then probably going to be fainter and you may not even see it. So we can sort of tell that probably these are almost certainly like very low inclinations here. So, of course, we have to take account of that when we're considering, you know, how many GRDs we should be detecting compared to the total number of radio galaxies.
So there isn't really any method to sort of
no, because because you can't. There's well, as far as I know, and Sarah might correct me here, that as far as I know, there's not much relationship between like any direction of rotation of your galaxy and the black hole in the center, as far as I know.
You could get a rough idea if we become comparing to a line scenario.
Right. Yeah. Exactly. Yeah, if there is one.
And then more sensitive radio data, like one low being thanks to the other. So building up that polarization information.
Yes, exactly. And it turns out that the jets of GRGs are almost always highly polarized. That was not our work, that was somebody else's work, but that's definitely something else we can look into. But yeah, like the emission lines, if they exist, but most of these are actually low, so it's hard to detect optical emission lines.
I was going to ask the same thing about jets in the line of sight. So
yeah,
it's been answered.
Okay.
So page 18 on the slide.
Page 18. So this was the H1 part, was it? What was your question? Yeah.
Yeah. Is there a reason why this page, I think they said before the galaxy, is there a reason why they're using that part of the sky?
You mean here?
Yes.
Don't know. Leia, go.
The continuum source.
Oh, yeah.
Bottom right of the field. So actually a lot of the detectors going up are false detectors because there's one constant gaps that in the so I'm still cleaning up this loss.
Oh, this one includes the 84 false detections.
Yeah.
Okay, so it's about, yeah, 84 false detections. Good question. Yes.
I have a question about this section where you mentioned that it's research means about high. I mean, they're pretty sophisticated source detection algorithms.
No, this is all automated. This is with Sophia 2, which is the automated source finding algorithm. So yeah, we did it, part of the team did it by eye just as a reality check to see how well we could get the automated source finder to work. But yeah, we're using this one called Sophia 2.
Okay, I think the next slide.
Before.
So when we change the plots images for different spectral.
This one?
Yeah, spectral, right? That's when you the frequencies.
Yep.
I think this is where it starts from low frequency, and there are some points low detection, and then later on we get detection.
Yes, there are, absolutely. So they're actually quite annoying. They're quite problematic, where you can kind of detect kind of one of the arms and then the other arm, but like not the center because there's probably maybe there's no H1 gas there for whatever reason, we're not detecting it. And then it's actually quite hard for the source finder to say this low frequency detection is the same as this higher frequency detection. It's the same galaxy, but there are different parameters we can tweak to get them to combine. And we think we've done it quite well now. But yeah, good question.
Okay, I don't see any more questions here. There is a comment on the chat about the video that I can. I will put the video, the recording video on the SAAO YouTube channel, so
Okay.
it will be up there.
Fantastic.
Okay, let's thank Jacinta again. Thank you so much, and see you in the next colloquium, everyone.